Hayward. I'm going to introduce Steve in a minute, but I'm on the MEG committee, and we're looking forward to having this presentation on the central interceptor by Steve from Watercare. There's a few housekeeping things which, if I get stuck on, I'm sure a couple of guys from Becker's are our hosts, and we'd like to thank them very much for this tonight. I'm sure they'll help me out, but in the event of an evacuation being needed, you go out of that door and take an immediate left and end up in that courtyard where you wait until cleared. In the loo, if you need to go to the toilet, you go out of that door, past the lifts, and you've got to get, if you're a gentleman, you've got to go past the ladies. There's a toilet door there. You go past that down into the gents area. If you're a lady, you can go straight into the ladies, of course. Now, when Steve's finished, and we get on to questions and answers, I'm going to hand this mic over to Simon Hall, who's a fellow member on the MEG committee, and he'll hand you this mic so that you can address Steve. Another issue for us, which I'd welcome you helping us with, is that the MEG enjoys a collaboration and affiliation with the Institution of Mechanical Engineers in the UK, as well as being a technical interest group under Engineering New Zealand. And we'd like to know who belongs to what. So could you please just raise your hand if you're an institution or I'm a key member and you've come directly. So that's 1, 2, 3. Any more? 4. So right, so that's 4 I'm a key members. You're both. You should just remember. Which one did you respond to, Brian? Was it right? So that's 5 then. Now, those who have come directly through the Engineering New Zealand, notice that's the rest, isn't it? So what about what about those who have just wandered in off the street then? Because there's a few who haven't put the hand up yet. No, what about you? You 3, are you? All right. So, but you did register for it. All right. So that's 3. Are you all of that? Okay. Very good. Welcome. Anybody else in a similar capacity to that? Okay. So we've got, what was it, 5? Very many ENZs and 3 visitors from the residents and social groups. Good. Thank you very much for that. Well, how many people are mechanical engineers, and how mechanical engineers as opposed to civils? Mechanicals. Well, that's about what, 60%. Civil who've come through civils. You're civil as well, Steve, aren't you? All right, it's about 20 or 30%. Good. Thanks for that. Sorry about that. Now, just as a point of clarification, as I'm doing this sort of warm-up act, it's a while since I had a microphone like this. It reminds me of my days in the working class clubs in Lancashire. So, where they used to start off and go, give order. So we've got your attention now. So who knows what an interceptor, the origins of the word interceptor were? And for the mechanical engineers here, that it's not a jet fighter or anything like that. Okay. So it's an old term. Watercare has 4 existing interceptors running towards Mangere sewage works. The term came into English usage in the 1850s with the scheme developed in London under Sir Joseph Bazalgette. And the River Thames was so badly polluted that it was suspected of all sorts of things, including the cholera epidemics. And so he came up with this scheme of running an interceptor along the north bank of the Thames and another one along the south bank, and intercepting all those foul sewers that were at that time flowing directly into the River Thames, which also used that water for drinking. So you can imagine it was pretty nasty stuff. And the interceptors then took the wastewater from the sewers towards the east until it reached a point where it could be discharged into the Thames, and then the tidal movement would take it out into the sea. So Watercare have devised this thing, and Steve will tell you all about it, to intercept sewers which would otherwise overflow or dump wastewater into where it wasn't wanted. So without more ado, I'll hand over to Steve, and please give him a warm hand.
Thank you, John. Can everyone hear me? Yep. Just by way of introduction, my name's Stephen Grace, and I've been working in the water industry for over 30. So my involvement with the Central Interceptor began probably in about 2009, when I used to work for one of the gentlemen over there, we were pulling together the information that was needed to do the design of the Central Interceptor, and that was for Metro Water. And subsequently, I became involved in 2014 as design manager for Watercare. And that was basically managing the team of consultants that were developing the design for us, and that comprised Jacobs, ACOM, and McMillan Jacobs Associates. So 5 years down the track, I'm still on the project and still working towards delivering it. So I'm going to run you through a bit about the project, specifically what it is, why it's needed, what the issues we're trying to address are, how we address those issues, where are we now, where are we going to next, and time for some questions. So essentially what it is it's a deep tunnel system, and there's many of these around the world. This one's a bit unique in that it both conveys and stores flow in the pipe. And as John said, it's intended to intercept a number of key overflow points that are scattered throughout the city. So it runs from Western Springs up in the north, actually goes to Grey Lynn now, and all the way south to the Mangere treatment plant, where we have a pump station that lifts the flow out of the deep tunnel into the plant headworks. And so it's gravity all the way. It's a 1 in 1,000 grade, and it's a 4.5 metre diameter pipe. There's also 2 link sewers. These are not small in their own right, so we call them link sewer B and C. There was an A and a D, but we managed to get rid of those in our design. So link sewer C is a 2.1 metre diameter pipe, and link sewer B is 2.4. So essentially this link sewer C goes out to Avondale, where it intercepts another pump station, and this one up here is in Mount Albert. So as you can see, it's pretty long. The original scheme to Western Springs was 13 kilometres. That by itself would have made it the longest tunnel in New Zealand. But with the additional link sewers and the extension to Grey Lynn, it's now almost 19 kilometres. So it's a very long tunnel. It's one that nobody will ever enter probably in its life, or we hope that will be the case, because it's a hazardous environment and it's very deep. The idea being that it's a low maintenance facility, gravity solution for addressing overflows and growth in the city. There are 16 deep shafts, and some of these are very deep, up to I think 76 metres is the deepest one. And they range in size from 3 metres up to about, the biggest drop shaft is going to be about 10 metres, and the pump station is 26 metres in diameter. The pump station, I know you're all mechanical engineers, so you'll be interested in things mechanical, has a 6 cubic capacity to pump out into the treatment plant, and that I'll talk a bit more about that. And there's quite a few connection sewers as well, and there's probably 50 odd chambers. They by themselves are not an inconsequential amount of work, particularly given the difficulty of connecting in an urban environment. And so they're probably $50 or $60 million just by themselves. The whole project has a value of 1.2 billion. So it's probably the biggest project Watercare's undertaken, certainly in the last 20 years it is. And by comparison, the cost of the City Rail Link, which seems to keep going up, is about 3.5 billion. So as I said, it's gravity sewer from Western Springs or Grey Lynn to Mangere. The reason why it's so deep is mainly because of geology. So in the north, we have a lot of basalt from the volcanic field. We have some in the south as well with Mangere Mountain. And so we've positioned the sewer underneath the basalt rock in the easily tunneled sandstones. For comparison, the rock can be up to 300 megapascals in strength, whereas the sandstone that is the bedrock of Auckland is more like 3 to 6 megapascals, so it's a much better material to be tunnelled. Main tunnel reaches, so they vary. They're up to sort of 4 kilometres for the southern part of the tunnel from Mangere up to Hillsborough. That number's just for the main tunnel, the 14.6. You can see that there's some quite long reaches here, which would make access for maintenance very difficult. The tunnel will be lined with concrete, and it will have an embedded HDPE liner for corrosion protection. This sort of segmental lining is pretty common in tunnels around the world. The link sewers will be pipes that will be jacked in the conventional pipe jacking microtunneling exercise. They'll be partially reinforced with steel rebar, and some of these segments, mainly through the sandstone reaches, will be just steel fibre, which is like a hairpin type fibre of steel that is impregnated into the concrete. And it has a 100-year design life. So why is this scheme needed? It's principally because we've got some pretty old assets that are in some vulnerable states. The Manukau siphon goes under the Manukau harbour, and that was laid in the 1960s, so it's coming up for 60, 70 years old. And that has always been a concern because it's laid on the sea-floor in a trench that was, they used a drag line to install it. And so it's exposed for being snagged by shipping and other things, but it's also exposed to the marine environment. So when we build our tunnel, we'll be 15 metres under the seafloor. That's the minimum depth, and so it'll be more protected. There's also a lot of growth projected in Auckland. We are currently sitting at about 1.5 million, and I think by 2030 we're expected to be 2 million. And we see a lot of that development, particularly in the catchments where we're going to be working around Mount Roskill and Mount Albert. And the catchments beyond that are also experiencing a lot of growth. So the Central Interceptor provides a spine network that we can then connect some of these overflows to and some of the other areas under growth pressure. But it also provides reinforcement for the rest of the network. So all of the area on the eastern bays will be relieved by us diverting some of the flow. I should have had a map of the entire scheme, but essentially at the moment the Ōrākei system takes water from Western Springs and takes it all the way through the city, right out to Glendowie, and then south through Otahu back to Mangere. So there's a big loop, which is a bit crazy. And it means that by the time the sewage gets to Mangere, it's quite septic. So we're taking it in a shorter route, more direct. And the third driver for the project is this juicing sewer overflows. So we have over 200 overflow points, mainly on the combined sewer network, that regularly spill into the harbour, Waitemata Harbour. and also some into the Manukau. So it's got a whole driver around environmental cleanup. This is a section of the Hillsborough Tunnel, so that runs under the Hillsborough Ridge. Our tunnel will duplicate this and ultimately replace it. The tunnel depth at that point is 110 metres below the Hillsborough Road Ridge. So you can see that the very traditional means of installing it and very inaccessible condition. This is the Lion Ave spillway in Mount Albert, and what you can see here is an overflow that occurred in 2016. It's good to compare it with the size of the gates on the overflow spillway, approximately 1 metre high. That's about a 4 cubic capacity that's flowing out into the Meola stream, and that's diluted with stormwater, but essentially it is combined sewage. So that happens very regularly, usually in a big downpour, but it can take relatively little rain for this spillway to trigger. I talked about the shafts. This is often described as a project of shafts rather than a tunnel, because it's the shafts that are the more complex elements. You can see there the depths, as I said, 78 metres at Keypay Park, so very deep, quite uncommon in a civil engineering context to be drilling shafts that deep, less so in a mining environment where they can go for a kilometre or more. As you might expect, we're using some of the modern tools. So we've got some 3D imagery. We use this for a lot for stakeholder engagement. So we can describe to stakeholders what's actually going to be built in their backyard. But we've also used it for safety and design and for planning construction. So these tools are really useful, and I've got an example of the pump station at the end of the slideshow. The drop shafts, there's 16 of them, and we went predominantly with a cascade drop shaft style of drop. So these have quite a few benefits. You can insert flows at any level. The alternative would have been to use a vortex drop shaft, and the vortex, you basically put it in at the top and it spins around as it goes down the chute, and you can't interrupt the flow on a vortex because it develops what they call an air core, which draws the air down into the tunnel. So there's a number of benefits to the cascade drop shaft. It has a wet side and a dry side. So the dry side we use for ventilation and pneumatic control, as well as for inspections. The wet side obviously carries the flow. Most of the shafts are big enough that we can drop a man cage down on a crane for inspection, but we do anticipate, and I'll talk a little bit about robotic inspection later, that technology will continue to evolve, and we're already using drones for monitoring construction progress. So we expect that in time we won't have to put people in these holes. We'll be able to send a robot down. There's a mention there about real-time control gates. So essentially we've got a number of gates on the scheme that control the inflow into the tunnel, and that's to stop the tunnel from overfilling. The situation where we reach tunnel soffit with the water being stored in the tunnel, if it happens rapidly, can result in a transient or a surge event, and that has quite a consequence in terms of the pneumatic performance of the tunnel. So the tunnel is always full. It's either full of water or it's full of air, and what we're trying to control there is how the air gets vented out of the tunnel. So as the water fills in the tunnel and it's evacuating air, if it happens rapidly, it can cause a surge wave, and it can actually cause a geysering effect where in other countries the top of the shafts has been blown off by the air pressure. And that can happen on quite large manholes and shafts. So I just springs to memory, there's one in Calgary of motorway, and the shaft lid is blown off and it's in the middle of the motorway. And it must have been a 3 or 4 metre diameter roof slab that's blown off. So they can be quite large defects. Also ventilation. So our aim is to prevent odorous gases escaping from the tunnel. So we have 2 air treatment facilities planned for this. One is a classic earth filter, biofilter, which treats it with air percolates through a soil layer and gets treated. And the other one is a biotrickling filter, which is a much more mechanical type of air treatment facility that's going to be designed by Armatech. This is a very slow video of the Cascade drop shaft physical model that we built at Auckland University. We did this in the fluids lab in Khyber Pass, and we tested a model of the Cascade drop that we tested about a dozen scenarios of tunnel full, tunnel empty, sudden and rush of flow, different introducing flow at different levels, just to prove to ourselves that it was the right tool for the job. And so that was quite a useful exercise, and it really brought the project to life as well, because we hadn't built anything at that stage. We had some drawings and thoughts, but we didn't actually have anything physical, so it was actually quite nice to have that. The link sewers, these are, as I said, quite sizable assets in their own right, and the one that is the longest is this one here, almost 1 kilometre long in a single drive. So that's it's not a world record, but in New Zealand it's quite a long way to jack a pipe. And as I say, they're over 2 metres, those pipes, so they're quite sizable in their own right. And I probably will skip over this, but just to say that the link sewer shafts are not shallow, they're quite deep in their own right, so 26, 28, 25, 31 metres deep. They're pretty deep in their own. So we're going to control the gates that control the inflow into the tunnel using the Mangere treatment plant system. The pump station at the treatment plant will be controlled on a Delta V Emerson system, which is what the plant uses. So the plant will control how the pump station operates and how much flow it takes into the headworks. We will have a digital microwave radio UHF control system for the gates that gets operated through a repeater on Sky Tower. And obviously there's a finite capacity in the tunnel. It's got about 240 cubic metres of storage. Once the tunnel is full, as I said before, we have to close the gates and spill to the environment. So we have a network discharge consent that requires us to meet a 2 to 6 spills per annum frequency and a volumetric limit on how much the central interceptor can spill as well. So there are a few controls. 240,000 cubic metres. 240 million litres if you talk in that parlance. And the gates are scattered throughout the city at different locations. Some of them require above ground structures, so we will be building some structures above ground. Plant rooms that will look probably not as engineeringly mundane as this. Some of them will have a public art treatment, which we're negotiating with Auckland Council. So we've got a number of requirements around those plant rooms. The gates themselves will be a mixture of electric actuation and hydraulic. The hydraulic actuation isn't common to water care. We would normally put in Rotork electric actuators, but the feeling was that some of the deeper gates are large and that we'd get a bit more power with a hydraulic system. And also they're more resilient in terms of they can operate with a minimal power input using solenoid controls. So they would have a stored nitrogen accumulator cylinder system that enables you to cycle through 2 open-close cycles before you run out of that stored energy. So it's just, the idea was these are going to be more resilient. we're going to get power outages in a storm when the tunnel's filling. We need something that's going to be a bit more capable of surviving that. And that's just a screenshot of a plant room concept. So the pump station is, again, quite a sizable structure. It's got a value of about $80 or $90 million. It's very similar to another pump station that I'll show you in a minute. And it's got a capacity of 6 cubic meters per second with 6 pumps. So these are not small pumps. And they are they're installed with a manifold that enables you to feed flow different ways into 2 large rising mains of a 1400 millimeter internal diameter. They're being built right now, and they have to feed their way through the treatment plant, which is very congested with services. John will know all about that. It's a portal frame building, and our consent requires us to have backup power supply. So we've extended the 11 kV ring main around the plant, so it actually now serves the pump station and the top end of the plant. But in addition to that, we're required to have an independent form of power. So we're going to be installing standby generators. I think there's 4 or 5 of them to provide a 5 MVA capacity to run the pumps. So it's quite a big structure with all of that. We also have an emergency pressure relief, which is it's in the event that the tunnel does overfill. It's not really to be used. I think in the consent hearing it was to be used once every 50 years, but it's not a small structure. It's 90 metres long and 11 metres wide. So it's quite a solid chunk of concrete that we're putting in there. And as I said, at May Road in Mangere, we have air treatment facilities. So that's a layout of the scheme at Mangere. If this works. So this is the pump station here. This is the biofilter. It's going to be one of the largest biofilter that Watercare operates. This is the emergency pressure relief, which is this big box culvert structure. And then we have twin rising mains heading off into the plant through a manifold. The design here is we call it a dual cell or a peanut shaped design. So the wet well is basically this half, and this is an inlet chamber that provides a number of things. It provides a space for the air ducting to come in from the biofilter. It provides a weir structure for the emergency pressure relief, and it also provides a bit of a surge chamber there as well. And then in elevation, we have the shaft is approximately 40 metres deep. I think it's 34 metres to the ground floor, but then you've got a 2 metre base slab. There's actually some little people here you can see who are operating valves or doing something. It just gives you an impression of the scale of this thing. Essentially, it's like a 10-story building underground. So water enters from the upstream left-hand side of the elevation, comes into this inlet chamber, and then it comes into a baffle structure, or it goes into the sump of the wet well, and then it gets pumped out and up out of the station. So we've done a few things with this. We've got a BIM model, which I'll show you at the end. So that's the top left. We set up a physical model for this, and we ran a couple of scenarios with it. So the physical model is essentially what's shown in the top right in the red. And so this has all been done in Singapore at the Nanyang Technological University. And they do a lot of this physical modelling. So like we did with the Cascade drop shaft, we also did a physical model of the pump station. And again, we ran a couple of scenarios. I think it was about 14. And so we have water entering at one end and coming through the inlet chamber, through the wet well, and up through the suction valve mouths and into the pump system. And essentially what we got out of this was we learnt that we were getting, there's a dividing wall between the two, and we were getting overtopping of it. So we raised the dividing wall. We proved that the pumps could draw sediment and material out, because there's a way that you can model little balls of plastic as sediment coming through the system. And we also modelled it at different levels in the inlet chamber and in the wet well, just to see how the thing was going to perform. So the Hydraulic Institute recommends that you either do CFD, or they say for pump stations of this size, you should do computational fluid dynamics analysis followed by physical modelling. And we said, well, we'll just do physical modelling, go straight to the solution. And as I said, Watercare does have a pump station that's very similar to this. So our pump station 64 Iraqi, the new pump station, which is called 86, is very similar in its layout. But there were a few things that we learnt from this about how to align things like the gantry crane above was not square to the shaft, and there were a whole bunch of lessons about how you put all the trunking for the cabling in, and where to put termination points and access for maintenance, that sort of thing. So we learned a lot of things from that. And as I said, this is the pumps at PS64. That's similar sort of scale to what we're going to be installing at the Mangere pump station. And I talked a little bit about the peanut dual cell shaft. So these are just some examples from the US. As I said, the pump station shaft is actually 26 meters in diameter. And I'm going to talk a little bit more about that. The inlet shaft is another 12-meter diameter shaft. So it's all pretty big stuff. So what we've been doing since late last year is we've been installing this large diameter shaft. So we had a machine imported from Germany, a Bauer machine, and that's the crane there. And there's a whole plant for bentonite slurry mixing and associated equipment. Trying to lean towards the mechanical engineering part at this point. So I'm hoping this will work. Oops. Sorry, that was a video, but it doesn't want to play. Anyway, it is going to play. So what it's doing here is it's got a mechanical head on it that grinds the ground and soil and breaks it up, and it's extracted using a series of pumps, and then it essentially it's all under a slurry, bentonite slurry mix to support the trench while you're doing it, and then you insert rebar cage, and then you put concrete pumped from the bottom with a Tremie pipe. So that's the other way I could show it to you. Multiple stages where you're inserting firstly the mechanical excavator and excavating these panels, and then you bring in the reinforcing cage, drop it in, and then you pump concrete in from the base. So this is work that's happened over the last, well, it was interrupted by COVID lockdown, but essentially been doing it since about January. And this is the machine that they brought in to do it. So it just gives you an idea of the size of it. 50-meter deep panels, 6 meters into the bedrock, 29 of the panels, 29 panels. I think that's just in the main shaft, the 26-meter one. 8,000 cubic meters of concrete, 590 tons of reinforcing, and then, as I said, the shaft diameters. So that was pretty much, wasn't quite 24-hour operation, but they did a day shift and a night shift. We've also just taken receipt of a training tunnel boring machine, which is to get the teams up to speed with how the machine that we're buying and will be delivered at the end of the year will operate. So this is actually a used machine that's been dismantled and reconfigured for training. And essentially the training that they'll be doing on it is changing out the tools on the cutter head, but also just getting familiar with the amount of access that they'll have getting in and out of the machine. So the tunnel boring machine that we expect to arrive in December is being made in Germany by Herring Connect. They made the machine for the Waterview Tunnel as well. And I believe City Rail Link are also getting theirs from there. It has a cutter head diameter of 5.4 meters. So our internal diameter is 4.5, but cut a hole and fill it with segments, it gets to be 5.4. It's got a mixture of disc cutters, scrapers, and the screw conveyor coming out the back is a 700 diameter screw conveyor. The total length of the TBM will be 165 meters. So that's with all of the cutting equipment, the bentonite mixing equipment, the controls, and all of the, there's a hyperbaric chamber, there's a safety refuge, which is a containerized, self-contained setup. If there's a fire on the TBM, they can escape into this refuge. The whole thing is controlled by laser guidance, and there will be an electric train that operates up in 2 or 3 electric locomotives that will bring segments in and take spoil out. So the spoil will go out on muck carts. And there's quite a few safety systems involved with these things as well, as you can imagine. So there's gas detection at the front of the machine, at the back of the gantry. There's a water curtain in case there's a fire, and that controls the smoke generation. So there's a lot. It's a very high-tech piece of equipment. But the company that's making it probably churns out, I don't know, 30, 40 of these things every year. I know that in Singapore, they require a new machine on every job, and sometimes they only do a kilometre. So, yeah, it's interesting business. So at the May Road shaft, which is where we're tunnelling to as our next work shaft from Mangere, we have 2 shafts, and they are 7.5 metre diameter, one in the middle of the screen, and then a larger 10 metre one at the top. So the smaller one receives flow from the link sewer that goes out to Avondale, and the bigger one will be the work shaft for tunnelling the northern part of the tunnel to Grey Lynn. We have a few other facilities there. There will be the air treatment and some supporting services. So that's the May Road site. I think it was last week. You can't really see very much, but in essence, the smaller of the 2 shafts has already been, they've installed secant piles, which is a wall of concrete columns in a circle. So they're ready now. They're just setting up the collar with the reinforcing cage. They'll pour that in the next couple of weeks, and then they'll be ready to excavate this down to 50 metres, roughly, which will probably be done with a clamshell system. And the activity at the north there is the second of the 2 shafts. That's the 10.5 metre one that will be used in the future for tunnelling north. So whereabouts are we? So we've got a timeline there. The consents were granted in 2012, and we completed detailed design in 2017. We went through a 2-year procurement process, and we awarded a contract in January of 2019, so a year and a bit ago. And we're aiming to complete the stage 1 construction to May Road by 2024, early 2024. and complete the stage 2 construction either late 2025 or early 2026. And that the time delay there is probably as much about the 1.6 kilometres extra that we're going to do to Greyland Tunnel. And as I said, we've got 4 sites active at the moment. There's the Mangere one, the May Road one, and we've got 2 others, and we're soon to start a 5th shaft site at Dundale Ave in Blockhouse Bay. So I was asked to talk a little bit about robotic inspection, and it's an interesting topic, but it's one that I'm not an expert in. But typically what Watercare would do is it would CCTV its trunk network on a 5-year cycle. And for that, our trunk network ranges from sewers that are 300 millimetres up to 3 metres. And some technologies available to do the smaller pipes, like little crawler robots, fitted out with cameras. And then separately, we would also do select sewers with laser profiling. So they would determine whether a pipe has gone oval shaped, if it's a round pipe. Not all our pipes are. Some of them are egg shaped, some of them are square. So yeah, but there is a piece of equipment that I actually have seen in the flesh at the Water New Zealand conference that is this Red Zone Super MD profiler. So it does a lot of things. It does laser and sonar, as well as CCTV. So that's quite a useful tool. It's installed on a drag line, so it's not autonomous, which would be probably ideal. I don't think Watercare has the appetite yet to put an autonomous robot in its sewers, for fear that it might never come back. We did put a sonar system through the Manukau siphon, and unfortunately the sonar head came loose from the unit, but it was retrieved at the downstream in a net. So the question was asked when we did geophysical drilling in the Manukau Harbour, who was going to insure the equipment, because the geophysical head was worth $40,000 and the owner was concerned he was going to lose it. So it is a consideration that you're putting expensive equipment down in a hole that you may never retrieve it from. So this one can do up to 3.2 metres. As I said, our pipe will be 4.5, but we can see the evolution of this equipment over time and see that we believe that by the time we built it, the technology will be available. And I saw it goes for 3,000 metres, so that's more than, well, it's almost as much as we expect to have in the southern section. It's 4.1 kilometres. But again, I'm sure that can be extended. I do know of a company in the US that's done 10 kilometres of an aqueduct in South America. So as I said, those are the specs: laser, sonar, CCTV, pan tilt, etc. It's a floating platform, and you can read it yourself. I'm a bit doubtful about the Wi-Fi connectivity item there. We have experimented with radios in our sewers, and obviously they need to be intrinsically safe because we're worried about sparks and flammable gases. But even with radios, you need a direct line of sight, so they're not perfect. So yeah, I'm not sure about the Wi-Fi there. So we are building this thing. We expect the TBM to arrive at the end of the year, and we'll start the tunnelling from Mangere in mid-2021, completing the southern tunnel and the link sewer mid-2023-ish, and commission it all by mid-24. The link sewer B and northern tunnel will commence in mid-2023. We'll get to the Greyland shaft about 2025, and we'll commission either late 2025 or early 26. So this is going to work. So this is the Mangere pump station. This is the video of the bin model that we had produced. So it just gives you a bit better visualization rather than the awful 2D CAD drawings I showed you earlier. So it's set up with a manifold so that you can alternate the pumps. So you don't have to run all of them at once. You can run them in different series. And it's got separation between the two sides of the dry well. It's a bit stilted, this video, unfortunately. It's probably, I thought if I ran it off my computer, it would be a bit smoother. So there's a few things that we continue to optimize. There were heat exchangers on the risers up the wall. We don't think we need those now because of the type of pumps that we're likely to select. And we won't have that many staff involved in operating the station. It'll be generally unmanned, as most of our pump stations are. And we're sort of working through the pump selection. There were 4 suppliers that we were looking at, and we've got it down to 2, but we're still to award the contract for that. So that is my presentation. So willing to take questions.
Right. Well, thank you, Steve. Just a point of order before you take over. I've promised Steve that we won't deal with any questions about the drought. And this gentleman here is a black belt in karate, taekwondo, anything like that. And he's allowed to hit anybody with this microphone who asks the wrong sort of question. So if you can hold that, and if you're all very nicely behaved, at an appropriate time, we might be able to persuade Watercare to talk about what they're doing in that direction on the clean water side. So I'll hand this to Simon Hall, and I'll thank Steve, and at the end of it, we've got a small gift which I'll present him with. So here you go.
All right, thanks John, and thanks Steve. So just while Andrew there lets us know if there's any questions on the in the interwebs. Just got one question for you, Steve, because I live pretty much midway between Keith Hay Park and Granny's Bay. Sort of interested in when you're going to be tunnelling under that sort of area.
Yes, so we should be at Hillsborough at the end of next year. But as I said, because of the Hillsborough Ridge, it'll be very deep, 110 metres at the Richardson Road intersection with Burrow. So I'd be very surprised if we hear any reports from you.
Okay,
Sensing
all right. Good to know. Thanks, Steve. All right, we got any questions from our physical audience?
This works, does it? Hey, a kilometre down along a long, narrow tube, the environment's going to be pretty damn awful. Are people wearing breathing gear the whole time? And I think you said you had a hyperbaric chamber. Is that an emergency thing, or is it actually where you're working?
Well, they've installed tunnels under the European Alps, and they go a lot deeper. So ventilation of the tunnel is always something that gets a lot of attention. And typically what they do is they'll push fresh air in from the tunnel portal. WorkSafe are all over it, particularly after Pike River. So we have some very strict regulations that we have to comply with. And we have to produce safety plans. They call them principal hazard management plans, specifically for ventilation and other mechanical, electrical details. So it's definitely well covered and heavily regulated.
Are they actually working in sealed rooms as such, or?
No, I went into the Waterview tunnel when they were building that, and no one was wearing respirators. But typically, these days you'd wear a self-rescuer, which is a little canister with a chemical in it. And I've used one of those. It's not very pleasant, and it doesn't give you much time. So that's why we've insisted in the specification for the TBM to have a refuge, and that I think you can stay in a refuge for about 48 hours, which is considered long enough for the fire to be extinguished. So as I said, Pike River really changed things in the New Zealand mining and civil infrastructure business. So any tunnels are very, and between us and City Rail Link, most of the tunnelling activity is in Auckland. So WorkSafe are actually establishing a mines rescue team to service Auckland. It's currently down in Hamilton because it used to be in the coal mines. They're actually bringing that team up to Auckland. And our contractor is going to establish their own rescue team as well.
You said the cost was about $1 billion, but the design life is only 100 years.
Yes.
It seems like a lot of money for something that's only going to last 100 years. What happens after that? Does it get refurbished, or does it have to be all ripped out and something else cool put in?
So Watercare puts 100 years on everything. That's kind of typical. And if you look around the world, most tunnels are designed for 100 or 120 years. Obviously, the hope is that it will last forever, but we know that these things don't. And I was telling some gentlemen earlier that I'm in that unfortunate position in my career where I'm starting to see things I built 30 years ago starting to fail or get demolished because they're redundant. And that's just the way it goes. The main thing I think is we're replacing infrastructure that's 100 years old. Some of the combined network and some of the central city suburbs was built over 100 years ago, around World War I. And that a lot of it is actually still functioning quite well. It's just under capacity. So you can't predict growth. And, we have boom and bust cycles economically. So we have building booms, and you just can't anticipate how long things are going to last, either from a hydraulic capacity perspective or from a physical asset perspective. But our hope is that it will last at least 100 years.
Hi, great talk. How much more capacity does what you're building replace what's currently there? And then, like you just said, you can't predict it, but what's the projection for 100 years from now, if there is one for capacity?
Yeah. So I showed you a photo of the Hillsborough Tunnel and the Manukau Siphon. The Manukau Siphon is roughly a 1,500 diameter pipe, and we're replacing it with a 4.5 meter diameter pipe. So we're increasing the capacity quite a lot. And a big reason for that is because we're taking combined sewage from the central area around Mount Eden and up to Greyland. And so we're plumbing a lot of that away from the problem areas. At the moment, it discharges into urban streams and into the harbours. So the intention is that we'll collect more, but that it'll be fed through the treatment plant. Essentially, the tunnel acts as a buffer because it's got so much storage in it. So that's the concept. But it's a combination of drivers, as I said, and meeting growth, dealing with legacy overflows. They're probably the two primary ones that we're trying to address.
Graham Coxhead here. The combined sewer that Auckland was built around, the separation programs that were put in place, are they still in place, and have they been taken into account in structuring the capacity of this?
So Graham, you'll remember there was a thing called the Drainage Strategic Plan that was developed in 2004, I think, and that was Auckland City's response to a lot of these issues. At the time, they anticipated it would cost about $2 billion to separate all of the catchments that were still separated, because they've been doing separation since the early 90s, I think, early 80s, actually. And the question is separation successful? Because there have been quite a few catchments where work has been done and it's actually gone backwards. Properties that were separated have become unseparated through development and a lack of regulation. So my understanding is that Auckland Council are policing it a lot better, so that doesn't happen anymore. But the question of whether we are going to continue to separate is, there are certainly catchments that are ripe for it. So although I've said we're going to take this tunnel to Grey Lynn, there are still plans to separate parts of Grey Lynn because they've already been partially separated and they've just got to finish the job. And then there's separation that happens through development. So at the moment, Housing New Zealand, or whatever they call themselves, Kaingaora, are doing a lot of redevelopment of their properties, particularly in Waterview, Mount Roskill, Owairaka, and they are actually doing separation as they go. So a lot of new development actually is a stimulus for more separation work to occur.
I noticed for the shaft design, you've got FRP. What sort of role does FRP play in the shaft design?
That's a good question. So we tendered it on this project on mostly concrete structures, but we invited the tenderers to be innovative and suggest alternatives. So when we went to tender, we had 2 shafts that were FRP, and the idea was that if we were to pre-drill the shafts under bentonite slurry, we could have a prefabricated FRP GRP liner that could just be inserted in the hole, and then you pump out the hole. So that's a lot quicker than having formwork and concrete pours and building the thing up from the ground. And it also meant that we could actually produce these in smaller diameters. We could hydraulically size them rather than size them for the construction activity. And it also meant we didn't have to put people deep down below ground because we could feed the GRP liners in from the surface. So as it stands, we've moved away from a lot of these structures being concrete. At last count, it's probably about 8 are now FRP, and they're going to be produced in Australia and shipped over. So we're working through the detailed design of some of those shop drawings of those elements now. But that's the intention, is that we'll move towards more FRP rather than less.
Thanks, Steve. My name's David Alders. A couple of questions. I think I detected from your presentation that there was going to be foul air withdrawn at May Road, and I guess from out at Mangere itself. Mm-hmm. And this was to be put through some sort of filtration.
Yes.
I think one of them was going to be earth filtration. Have you got some sort of specification for that exhaust? Or probably from the point of view of resource consent.
Yes.
For that.
Yeah.
The other question I have is that until quite recently, there was going to be on the Waterley foreshore a vent, mm-hmm. which caused quite a lot of local angst.
Yes.
There, and then it suddenly vanished, found not to be necessary. Mm-hmm. Could you just give me or the company, or the business's thinking about why that was able to be removed?
Yep.
Thank you.
So the consents for odour discharges say that there's to be no objectionable odours at the boundary of the properties. So that some of the shafts are in parks, and you start to say, well, where's the boundary? People could be walking past this structure, and if they're right on top of it, because we're not able to prevent people from walking on top of them, then there's a zero boundary, if you like, no distance to boundary whatsoever. So we chose to put the air treatment facilities in properties that Watercare owns. So May Road, we probably have 40 metres to the boundary before we hit the residential properties adjacent. And the specification it's very difficult to say what does no objectionable odours sound like. Or, everyone, it's very subjective. Watercare does taste and odour surveys of drinking water, and we have a panel that assesses it. And these are people with special noses. They're like wine connoisseurs. So the question of, well, what's the specification for odour treatment? essentially there's a system of odour units, and the depending on how you model it, because what we've done is we installed weather stations at each of the sites to understand the local climate, the microclimate. So we've got wind speed, we've got humidity, we've got temperature, we've got rainfall, and we modelled it all in a atmospheric model, dispersion model, and we decided that you've got to try and turn something that's very vague, no objectionable odour, into something engineers understand and can actually calculate and mathematically produce a result. And so we ended up setting ourselves a target of 1 odour unit at the boundary, and that's achieved through treatment and through dispersion. So it's a combination of the two. And your second question? Right, yes, Kiwi Esplanade. Yep, so the Kiwi Esplanade shaft was a mixture of things. So I said we have a link sewer C and a link sewer B. We also had a link sewer A and a link sewer D. Link sewer A crossed Western Springs Park near the lake and the zoo, and we found the geology there was very difficult. So we said, well, that's going to be a challenge. We might even intercept the lake. We don't want to drain the lake into the tunnel, so let's not do that one. And we found a way that we can divert those flows through the Oraki main sewer to Grey Lynn and intercept it at Tairiki Street. On the Kiwi Esplanade one, we had a similar thing where we said, okay, we know we've got consent to do this, but do we need to do it? And there were a couple of things driving the need for a vent there. We were going to divert flow from Mangere Bridge into the shaft, and we understood that wherever we put a shaft in, we'd need to provide a pressure relief vent. Plus, we thought there was a possibility that as the water filled the tunnel, there could be a air bubble travel back up the pipe, and it would then vent at that location. So we had to put an air treatment facility there. Another reason for having a shaft there was because we thought, well, before we go under the harbour, let's inspect the machine and see that it's in healthy condition before we go under the harbour. So what we've agreed is we can actually inspect the machine before we go under the harbour without a shaft. We can divert the flow that was going to that shaft back into the Western Interceptor and take it directly to the plant. It's only about 40 litres a second, which is quite doable. And the geology around Kiwi Esplanade, as you'll see it on the foreshore, there's a lot of rock. So it would have made it very noisy, very disruptive to install a connection sewer there. So we just looked at it after thinking about it a lot and thinking about the possibility of this air bubble and inspection of the machine and all the other things, and said, actually, if we don't build a shaft, we don't have half those problems, so let's not build it. And we just said we won't do it. So it wasn't just a case of, oh, it's too hard, we won't build it. It was through an assessment of saying, well, what is the risk of not being able to do the inspection before we go under the harbour? We can do that under hyperbaric conditions if we have to, and all the other things I've talked about. So there's a logic. There was a logic behind it.
Just check in, Andrew. Any questions on the chat there?
This is quite a comprehensive sewer network. Do you have a central control and monitoring station? And where will that be?
Yeah, so Watercare has a central control room at Newmarket. So that's in our head office there. And we have backup stations, mainly at Mangere, but there's one at Huia, there's a few others. So essentially they're all controlled from a central point, but we have backup stations. Does that answer your question?
We've got one question online. Do you consider decentralised treatment as an alternative?
So Watercare and all of the and localised treatment was considered. In fact, I often say that our Chief Executive, Raveen Jadaram, did his master's thesis on the possibility of doing localised treatment. But it's difficult to maintain in a heavily built up urban environment. In fact, the site where Raveen did his thesis now has a 5-storey apartment building next door to it. So maintaining that in an intensely developed area is very difficult. So I must admit, I went to Hong Kong and talked to the operators there, and they clean out primary screening facilities in downtown Hong Kong, and that's before it goes into a tunnel under the harbour. I was quite surprised that they didn't have odour complaints, but they must have systems to manage that. So the other thing about decentralised treatment is every facility has to be maintained to a high standard. So depending on how many satellite plants you've got, it becomes quite uneconomic.
All right. Do we any further questions? All right. Well, I've just got one more. I happened to notice on your wee fly through of the Mangere treatment plant video, you had Darth Vader sitting there at about ground level. Do you have any staffing contingency plans if you're not able to secure Darth Vader to run that part of the system?
So we have a few comedians in our design team, and we've just let it be.
All right, very good. Thanks. I'll just hand back to John then.
You.
It's always good to end on a humorous note. I think I'd like to thank you all for your participation and keen interest. And I'd like on your behalf to present Steve with a token of our appreciation. So if you give him a good final vote of thanks.